How Linux works. The journey of a simple ls command. Introduction. Linux architecture. Before we follow the ls command, let's first understand Linux architecture. Linux is built around a simple but powerful design. Applications run in user space. Hardware exists at the lowest layer. Between them sits the Linux kernel. Applications cannot directly access memory, disks, networks, or devices. Instead, they communicate with the kernel through system calls. The kernel manages processes, memory, file systems, networking, and hardware devices. In simple terms, applications talk to the kernel. The kernel talks to the hardware. The hardware performs the work. Now let's see what really happens when a user types a simple command, ls. Although it looks simple, this command will travel through nearly every major subsystem inside Linux. Step 1. User types command. Our journey begins when the user opens a terminal window and types ls, then the enter key is pressed. To the user, this feels like a simple action. But behind the scenes, Linux is about to perform dozens of operations. Everything starts with these two characters. Step 2. Shell receives input. The terminal itself does not execute commands. Its job is only to display text and collect keyboard input. When enter is pressed, the command is passed to the shell. The shell, usually bash or zsh, becomes responsible for interpreting the command. The shell now begins deciding how to execute the user's request. Step 3. Shell finds program. The shell must locate the executable file. To do this, it searches the directories listed in the path environment variable. Linux checks directories such as /usr/local/bin/usr/bin/bin. Eventually it finds /bin/ls. The shell now knows exactly which executable should be launched. Step 4. Create child process. The shell does not replace itself. Instead, it creates a new process. Linux performs this operation using fork. The original shell continues to exist. A new child process is created. This child process will become the ls command. Process creation is one of the most fundamental operations in Linux. Step 5. Load ls program. The child process is still a copy of the shell. Linux now executes exec. This system call replaces the shellcode with the contents of the ls executable. The process remains alive. But it is no longer a shell. It has officially become the ls program. Step 6. Load executable into memory. The kernel now loads the ELF executable into memory. Linux creates a virtual address space. Several memory regions are prepared. Code, data, heap, stack. The program is now fully loaded and ready to run. Step 7. Scheduler assigns CPU. Many processes are running simultaneously. The Linux scheduler decides which process receives CPU time. The new ls process is placed into the run queue. When its turn arrives, the scheduler assigns CPU resources to it. The process can finally begin executing instructions. Step 8. CPU begins executing ls. The CPU starts executing machine instructions from the ls program. Instructions are fetched, decoded, and executed. The program initializes itself and prepares to perform its task. Very quickly, ls discovers that it needs directory information. But that information belongs to the kernel. The program must ask Linux for help. Step 9. ls needs directory data. The purpose of ls is to display files and directories. To do that, it needs directory entries. However, user space programs cannot directly access storage devices. Only the kernel can do that. The ls process prepares to request information from Linux. This is where the journey enters the operating system itself. Step 10. Request directory information. The ls program performs a system call. Typically, Linux uses getDens64. This system call requests directory entries from the kernel. The CPU prepares to switch execution from user space into kernel space. Control is now transferred to Linux. Step 11. Kernel takes control. The CPU enters kernel mode. The current user space context is saved. The kernel begins running on behalf of the ls process. The request is now completely under kernel control. The Linux kernel must determine how to handle the system call. Step 12. System call handler. Linux examines the system call number. It looks up the appropriate handler in the system call table. The kernel locates sys_getDense64. This function is responsible for retrieving directory entries. The file system subsystem is now engaged. Step 13. VFS receives request. The request enters the virtual file system, or VFS. Linux supports many file systems. Extension 4. XFS, BTRFS, NFS. Applications should not need to know which one is being used. The VFS provides a common interface and hides implementation details. Step 14. Locate directory. Linux must locate the directory being listed. Internally, directories are represented using inodes. The kernel finds the inode corresponding to the current directory. Once the directory has been located, Linux can begin retrieving its contents. Step 15. Check page cache. Before accessing storage, Linux checks the page cache. The page cache stores recently used file system data in RAM. Memory is much faster than storage devices. If the directory data is already cached, Linux can return it immediately. If not, Linux must retrieve it from storage. Step 16. Cache hit or cache miss. If the data exists in memory, Linux performs a cache hit. The information can be returned instantly. If the data is not cached, a cache miss occurs. Linux must read the directory information from the file system. Either way, the goal is the same. Retrieve the directory entries. Step 17. Read directory entries. The file system reads the directory records. Each directory entry contains information such as file names and inode references. Linux gathers the requested information and prepares it for return. The kernel now has the directory entries needed by the ls command. Step 18. Return data to kernel. The file system returns the directory information to kernel buffers. The data is now available inside kernel space. Linux verifies the operation and prepares to return the results to the waiting application. The request is almost complete. Step 19. Copy to user space. The kernel copies the directory entries from kernel space into memory owned by the ls process. This transfer crosses the user space and kernel space boundary. The system call completes. Control returns to the ls process. Step 20. ls receives data. The ls program now has access to the directory entries. For the first time, it knows what files and directories exist. The retrieval phase is complete. The presentation phase begins. Step 21. Format output. The raw directory entries are not designed for humans. The ls program formats the information. It may sort entries alphabetically. It may apply colors. It may organize output into columns. The data is transformed into a readable form. Step 22. Write to terminal. The formatted output must now be displayed. The ls program performs another system call. Using write, it sends the text to the terminal. The kernel routes the output to the appropriate terminal device. Step 23. Terminal displays result. The terminal receives the formatted text. It renders characters on the screen. Finally, the user sees, documents, downloads, pictures, videos, projects. The command has completed successfully. Conclusion. What just happened? A simple ls command traveled through the entire Linux stack. The shell interpreted the command. The kernel loaded the program. The scheduler assigns CPU time. The CPU executed instructions. A system call entered the kernel. The virtual file system processed the request. Directory entries were retrieved. The data returned to user space. The output was formatted and displayed. All of this happened in just a few milliseconds. This journey demonstrates how Linux really works. Applications talk to the kernel. The kernel talks to the hardware. And Linux coordinates everything in between. That is how Linux works.